Before any skyscraper scrapes the sky or any bridge spans a river, something powerful must hold it up. Deep underground. And that hidden hero? The PHC pile. Today, we're stepping inside a massive industrial factory to uncover how these high-strength concrete columns are made. Step by step, from bundles of steel to the solid foundations that carry the world's heaviest structures. This is engineering perfection in motion. Let's dive in. Every PHC pile begins with a bundle of metal bars, but not just any steel. These are PC steel bars, short for pre-stressed concrete steel. Each strand is engineered to handle extreme tension. Once locked inside concrete, they form the internal spine that gives a PHC pile its legendary strength. Fresh steel arrives at the factory in long, raw lengths. Workers unload it and feed it straight into a cutting machine, a roaring system of high-speed blades and mechanical clamps. The machine slices every bar down to the exact specification required for each pile design, accurate to the millimeter. After cutting, the steel bars move to the end heading station, where heat and pressure transform both ends. Electric headers deform the tips into gripping heads, the crucial anchors that hold under massive tension later during pre-stressing. Next comes one of the most mesmerizing machines in the whole factory, the automatic rebar knitting system. Imagine a giant rotating hoop, a robotic loom made for metal. Technicians carefully position the vertical PC bars into slots on a circular steel jig. Then, like a mechanical spider, the knitting machine welds thin, pencil-sized steel rings around the bars, one after another, evenly spaced. These circular rings are what give the skeleton its perfect alignment and rigidity. When the welding is finished, the frame now looks like a hollow steel cylinder, the future heart of the PHC pile. Workers remove it from the knitting station and place it into a round base jig. This heavy jig clamps the frame with bolts and adjustable arms, ensuring that the steel stays perfectly centered and stable. It also doubles as a mold interface for the concrete casting process that's about to begin. Now comes the concrete, the substance that gives the pile its body. A massive crane arm lifts the jig, still holding the steel skeleton, and carefully lowers it into the bottom half of a steel mold. Each mold is a long, heavy-duty cylinder split into two halves, designed to withstand intense vibration, pressure, and heat. With the skeleton in place, workers pour in the concrete mix. The gray slurry flows around the steel cage, filling every gap. Meanwhile, a rotating vibrator runs along the mold, shaking the mixture to release trapped air bubbles and ensure perfect compaction. The goal here: no voids, no weak spots, just smooth, dense concrete wrapped tightly around its steel core. Once the bottom half is filled, the top section of the mold is lifted into position by an overhead crane. Automated fasteners then clamp it shut with precision torque. A line of robotic wrenches runs along the mold's length, tightening each bolt uniformly to prepare for the next step, the most critical phase of all. Here's where PHC piles separate themselves from ordinary concrete columns. The sealed mold is hoisted into a centrifugal casting machine. Imagine a giant horizontal barrel spinning at blinding speeds. As the mold begins to rotate, centrifugal force pushes the heavy concrete outward toward the mold walls. The water and lighter materials are driven inward and drained away. This process compresses the concrete into a super dense outer shell, forming a smooth, rock-hard surface. That dense outer layer is what allows PHC piles to resist corrosion, water intrusion, and underground chemical attack, even after decades of use. For several minutes, the mold spins at high RPM, the concrete inside transforming under pressure and motion. Then, the rotation slows, the mold is released, and it's wheeled out to the curing area, ready for the next transformation. The newly formed molds are rolled into a steam curing chamber, a massive steel container that looks like an industrial oven. Inside, dozens of molds are stacked like giant metal logs. Once sealed, the chamber fills with high-temperature, high-moisture steam. This accelerates the hydration process, the chemical reaction that hardens concrete. The controlled humidity prevents cracking and ensures every inch of the pile cures evenly. After several hours, the chamber opens with a hiss of vapor. The result? Concrete that's no longer soft or gray and wet, but solid, dense, and strong enough to be handled. But there's one more critical transformation before it can truly be called a PHC pile. At this point, the pile looks finished, but it isn't yet a PHC pile, not until it's pre-stressed. Pre-stressing is what gives these piles their incredible strength. It's a simple but brilliant idea. Stretch the internal steel bars inside the hardened concrete so that the steel always tries to pull inward while the concrete resists outward. This locked-in tension creates permanent compressive strength throughout the pile, allowing it to handle massive loads without cracking or bending. To do this, workers unbolt the mold using an automatic bolt remover, a specialized tool that runs along the mold, loosening every fastener quickly and evenly. Once the top half lifts away, the exposed concrete column is hoisted, still attached to its jig, to the hydraulic stressing station. Here, huge hydraulic arms grip both ends of the pile. The internal PC steel bars are stretched under thousands of pounds of pressure. While the bars are under tension, the surrounding concrete holds them firmly in place. The moment the force is released, the steel wants to contract, but it can't. The concrete's resistance traps that energy inside, permanently reinforcing the pile from within. That's the power of pre-stressing, the secret behind why PHC piles can survive decades underground, supporting skyscrapers, bridges, and tunnels under unimaginable forces. Once tensioning is complete, the pile is released, the jig is disassembled, cleaned, and prepped for the next production cycle. Every component is reused with precision, efficiency that keeps the factory running around the clock. Now that the pile is structurally complete, it moves down the line to the automatic labeling station. Here, robotic arms print detailed technical information directly onto the concrete surface, including batch number, strength rating, manufacturing date, and dimensions, all using waterproof industrial ink. From there, the piles are paired and lifted into pressurized heat curing chambers for a final round of curing. Think of it as a precision oven that finishes the job. Steam curing started. Inside, the piles are exposed to carefully controlled heat and pressure, finalizing the hydration process. This step strengthens the microscopic bonds between cement and steel, locking everything together into a single, unified structure. After hours in this controlled environment, the piles emerge stronger, tougher, and ready to face real-world stresses. PHC piles were first developed in Japan in the 1950s, a time when cities were growing rapidly upward, and engineers needed foundation systems that could handle both heavy loads and frequent earthquakes. Traditional driven piles made on-site couldn't deliver the consistency or strength that modern structures demanded. So Japanese engineers came up with something revolutionary: factory-made, pre-stressed, high-strength concrete piles, manufactured under strict quality control and formed using centrifugal casting. The idea spread quickly across Asia and then worldwide. Today, PHC piles are everywhere, from subway tunnels in Seoul to offshore piers in Singapore to high-rise foundations in New York and Dubai. The same process, the spinning, steaming, and stressing, continues to define the gold standard for modern deep foundations. Interestingly, the centrifugal casting concept that defines PHC piles wasn't originally from construction at all. It was inspired by industrial centrifuges used in mining, machines that separate ore from mud using pure spinning force. Engineers realized that if centrifuges could separate materials with precision, they could also be used to compact concrete, creating denser, stronger, more durable structures. And that's exactly what happened. With strength perfected, the final step is protection. Each pile's exposed steel base receives a protective coating, either enamel or industrial paint, depending on its final use. This coating shields against corrosion, especially critical for piles destined for wet or coastal environments. It also improves adhesion if the pile will later be anchored using grout or resin during installation. Once coated, the finished PHC piles, now fully cured, labeled, and inspected, are lifted by gantry cranes and carefully loaded onto flatbed trucks. Stacks of massive gray columns, each several meters long, are strapped down securely and prepared for shipment to construction sites around the world. There, they'll be driven deep into the ground using hydraulic hammers, forming the invisible but vital skeletons beneath skyscrapers, bridges, and industrial plants. From a few bars of steel and a bucket of concrete to a masterpiece of precision engineering, the making of a PHC pile is a story of science, machinery, and craftsmanship working perfectly together. Every spin, every weld, every blast of steam and ounce of tension, it all builds toward one purpose: creating the strongest, most reliable foundation material on Earth. By the time a PHC pile leaves the factory, it's been cut, welded, cast, spun, steamed, stretched, baked, and branded, compressed to the limits of material science, all so that the buildings we live and work in have something solid to stand on. If you enjoyed this deep dive into the world of industrial concrete and heavy manufacturing, don't forget to like, share, and subscribe for more behind-the-scenes stories from the factories that build the modern world. Because before any city rises, something has to hold it up. And now, you know what that something is.